So today we're going to start looking at how the Earth is put together, and we're going to start off with the layered structure of our planet. This is going to work a little bit different than it has in the past. You are not going to take notes on scratch paper. Instead, I'm giving you this guided note sheet, and as you listen through this presentation, you have to listen carefully to the key points and such that I'm going to outline for you and determine where those are going to fit in on this sheet. I'm going to very much stress what I need you to know and where I want you to put it in on this sheet. So you have to listen very, very carefully. You must watch the video in order to complete this. All right, so the Earth has 3 or maybe 4 main layers. We have the crust, the mantle, and the core. This is pretty much a rehash from both elementary school and middle school. First of all, let's start talking about the crust. The crust is, by definition, first layer, the crust, the thin, rocky outer layer of the planet. It is also the smallest layer of our planet. Now, that crust is divided up into 2 distinctly different types of crust because the crust isn't the same the whole way around. We have the oceanic crust and we have the continental crust. Now, the big difference between these is the continental crust is not very dense rocks. They're kind of lighter, fluffier rocks, whereas the oceanic crust is made up of the heavier rocks and minerals, the more dense rocks and minerals. This is the reason why the ocean crust is at the bottom of the ocean, because it's heavier. It's going to sink lower into the planet than the continental crust, which is lighter, less dense minerals, considered to be like styrofoam versus wood floating in water. The styrofoam is less dense, so it rides up higher. The wood rides lower. The same is true of the continental and the oceanic crust. The heavier ocean crust goes to the bottom. That's why it's on the bottom of the ocean. Whereas the continental crust is lighter, fluffier rocks, so it rides up higher, sticks up out of the water, hence our continents. The thickness, relative thickness, the continental crust averages about 25 miles thick because the rocks are relatively kind of light and fluffy. They're spread out. Whereas the oceanic crust is only about 4.5 miles thick because it's so dense it squeezes itself into a very, very small layer. Now, for some sense of scale, because it's very hard to depict things on our planet when we're on the planet itself. If you've ever been to the Grand Canyon, certainly you've seen pictures of it. The average depth of the Grand Canyon is only about 1 mile. Now, keep in mind the continental crust is 25 miles thick, so this barely scratches the surface. But we can go into the crust. Well, the world's deepest mine, a gold mine in South Africa, goes about 2.4 miles underground, so only about 10% of the way into the crust. So this mine is way down there. It's so deep that they have to use air conditioning to cool it. Miners working in there, it can get up to 131 degrees. So how deep have we gone into the crust? Well, in the course of scientific exploration, we have drilled down into the planet and we've tried to get down there and see what's in the different Earth layers, and the Soviet Union managed to get down about 12,261 meters, or about 7.5 miles, and that is the deepest that man has ever gone into our planet. 7.5 miles, and that was with a 2-inch super tough diamond drill bit. We couldn't go any deeper than that because the rocks just get too tough and it gets to be too hot, and anything that we've got on the surface just melts under the intense heat and pressure as we go down there. So the big point here is the deepest we've ever gone is about 7.5 miles, which is about 0.19% of the way to the center of the Earth. So we haven't gone very far. We've gone less than 0.2% of the way into our planet. So for a sense of scale, here's what this really looks like. This is the relative sizes. The crust, you notice, is basically that thin black line at the top. So it's a very, very small portion of the Earth's mass. So all of these movies, Journey to the Center of the Earth, the book, or the movie The Core, or the movie Journey to the Center of the Earth, all totally fake, impossible science. We've only been down there about 7.5 miles with a drill bit. So nothing like this is even possible. So let's start talking about the mantle. The mantle is the layer that is between the crust and the core. It is 82%. It is 82% of the Earth's mass and volume. So it's the biggest part. It is about 1,500 miles thick. it ranges in temperature from at the top where it's cool, it's about 500 degrees Celsius, to down near its bottom part where we're getting close to the core, up to about 4,000 degrees Celsius. So big point here is the deeper you go, the hotter it gets. One thing about the mantle, you have to understand, a very key point is that the mantle is not rock. The crust is rock, because the crust is cool, and rocks, when they get cool, they harden and they turn into rocks like we know it. The mantle is rocky material, but it's not rocks like we know about it. Know them. The mantle is more like gooey rocks, more like rocks that have turned into Play-Doh. A big point about the mantle is that the deeper you go into it, the hotter it gets. So we'll go down to the core, and the core has two parts. It has an outer core and it has an inner core. Now both of these cores are made of the same material. The core is made up of iron and nickel, and it is super, super hot. The inner core, we'll do this part here first. Some notes about the inner core is that it's solid. It is about 7,000 degrees Celsius, and it is about 750 miles in diameter. Now the outer core is about 1,400 miles thick. So it's bigger, but the thing about the outer core that makes it so unique is that it is a liquid. It is about 4,000 to 7,000 degrees, but it remains a liquid, whereas the inner core is a solid, because the inner core is so far down there that even though it's hot enough to be a liquid, it can't be because it's under so much pressure. It just squeezes everything together and makes it a solid. So the composition of each layer. The crust is rocks. Notice a fairly low density, 2.7. The mantle is iron, magnesium. It's molten, gooey kind of stuff. And the core is iron and nickel that is super, super hot. The key idea here, once again, is that the deeper you go into the earth, the higher the density. Now we have a more modern, different way to look at the earth. The crust mantle core is kind of a old school, kind of traditional way of looking at it, but we have this new kind of description, and we base our layers more on how the materials act. We divide the two outermost layers into what we call the lithosphere and the asthenosphere. The lithosphere is the hard outer layer. It is the crust and the top of the mantle, which is still kind of crusty and hard. Whereas the asthenosphere is the gooey layer that's underneath the hard shell. And that becomes very important in a few slides. So the lithosphere, it is the hard outside of the earth. It is the crust and the top of the mantle. The asthenosphere is that gooey layer just underneath the hard outer layer, where rocks are a little bit more plastic. I like the word gooey because you know what that means and you can picture what that means. Now, we get some movements because we got this gooey stuff that is not necessarily locked in place. We can have some movement of the Earth's crust. And the first guy to propose this was this guy named Alfred Wegner. And he was in the early 1900s, and he produced a new radical idea. This is the idea that the top of the earth was moving around on top of this gooey layer underneath. And because of that, he had this idea that all of the land masses, all the continents, were stuck together at one time, and they have now kind of slid apart from one another. They're sliding around on that gooey layer, and that eventually they're all going to come back together again. So he called that landmass, with all of the continents together, Pangea. And it was part of his idea of continental drift. And the theory of continental drift is that the continents are moving around, and they have been together as one landmass about 250 million years ago before they started to drift apart. Now, people did not think much of Wegener's ideas in the early 1900s. Most scientists of his time did not accept it because he could not explain how the continents were moving. He was basically laughed at by the scientific community of his day. Now, it's very important because now we kind of know that this guy was right. The question becomes, what has changed since the time that he first introduced his theory? Well, after World War II especially, and we had things like sonar and radar that were developed and used quite extensively in the war effort, after the war people started looking in taking that technology and pointing it at the Earth and learning more about the Earth. And then, especially in the 1960s, and we had submarines and checking out the differences between the ocean crust and the land crust, and we could tell what's going on underneath the crust. People started to figure out, hey, you know what? Maybe that guy was right. And it's really quite amazing to think that this guy proposed a theory in 1912, and it wasn't proven until 50 years later, long after he had passed away. So he's one of these great scientific minds that was way ahead of his time. So we've got Pangaea as the name that he gave to all of the continents together. It comes from a Greek root meaning entire, and Gea meaning earth, so all earth together. Now, he didn't just come up with this out of the blue. He actually looked at some different pieces of evidence that supported his idea, and we're going to look at them. First of all, the first piece is the fact that the continents kind of look like puzzle pieces, especially South America and Africa. If you've ever sat there and daydreamed, look at a globe, you kind of see how they kind of fit together. That could be just coincidence, but it was the first thing, the first little piece of evidence that maybe got him thinking. The second, more important one is the fossil record. And there are a couple key fossils that he looked at, but the most famous one is the Mesosaurus. And the Mesosaurus was a freshwater kind of dinosaur, what we would think of like a crocodile. It would be the best analogy, or alligator. Now here's the trick with the Mesosaurus. It was found in Africa and it was found in South America. Identical fossils, the same organism, but we know that this organism was a strictly freshwater creature, meaning there's no way that it swam all the way across the ocean from Africa to South America, which kind of led credence to the idea that, hey, Africa and South America must have been together at one time. And that's what you see right here. Here's our Mesosaurus. And there are other fossils where we found similar patterns across not just Africa and South America, but other continents, and not just animals, plants as well. So that was the second piece of evidence. Rock patterns. Just like fossils of animals, fossils of rocks or similar rocks, we know have similar parents, and we can tell when one rock is related to another. And these mountains here in Norway are very much the same rock as our Appalachian Mountains. So that lends credence to the fact that these two mountains were together at one time, like this was one end and this was the other end. And here's kind of what it looked like with North America, and here are the mountains up here, and here's our Appalachian Mountains, and they were all one mountain range. The only way that could have happened would have been if all the continents were together. Ancient climate patterns is the fourth piece of evidence. We've got rainforests and swamps in Canada. We know there were, but Canada is way too far north. This supports the idea that Canada must have been near the equator at one time. We also know that Australia had some glaciers at one time. Now we know Australia is too far away from the South Pole now, but that means at one time it was more south than it is today, because we know Australia can't have glaciers. So we've got these four pieces of evidence: the jigsaw puzzle pieces, similar fossils, ancient climate patterns, and similar rock patterns across the ocean. So, was Wegener correct? Did he have the right idea? The answer is yes and no. He really proposed the idea of continental drift, but continents aren't actually sliding around. The more correct idea is this idea of plate tectonic theory. And this is what Wegener's ideas were morphed into once we had a better understanding of what was going on under the ground. A tectonic plate is a large section of the Earth's crust, not just a continent. And tectonic plate theory is the idea that these plates are constantly sliding around on top of something that is hotter and gooier underneath it. Wegener thought the continents were the individual puzzle pieces. Turns out they weren't. That the Earth is divided into these major tectonic plates. So the crust in the ocean can be connected to the crust in the land, and they slide around together. Now, Wegener couldn't have done this in 1912. He didn't have submarines. He wasn't out there tooling around the bottom of the ocean. He couldn't look at the ocean crust. He certainly didn't have sonar and things like that and certain satellite images to help map things. But he had a good starting idea, and it's amazing that it took 50 years for technology to catch up with and prove what he came up with in just his mind. So the difference between plate tectonics and continental drift, just the continents. It's not correct. Plate tectonics is the idea that there's large sections of the entire crust, both the land and the water. That is the more correct, and that is the scientifically correct term. Now, how do continents move? Basically, this idea of slab pull. We know that there's heat underneath, and we have that gooey layer underneath. So as things just start sliding around, they're able to slide on top of that gooey layer, and that's how the plates are able to move. A boundary is where we have these two distinctly different plates meeting. Remember, these plates are moving around. Sometimes they're moving towards each other, sometimes they're moving away from each other, sometimes they might not be moving at all. They might be static and kind of just sitting in place. So we have some very distinct different boundaries where the plates come together. The first is called a convergent boundary. To converge means to come together. So a convergent boundary is where two plates are moving towards each other. A divergent, where you diverge, you're going away from one another. So a divergent boundary is where plates are moving apart. A transform boundary is where the plates are not moving towards or away from each other, but they're kind of sliding past each other. Depending on the plate boundary, you get very different shapes to the land. And one of the reasons why we have different shaped land is because these plates have been hitting and pulling apart for millions and millions of years, and that's why we have different shapes of the land. First of all, a convergent boundary. Two plates move together. So when they hit, one plate's got to go up and the other plate has to go down. They both can't be in the same place at the same time. Well, this particular action where one plate goes down and the other one goes up has a name. It is called subduction. Subduction is the act of one plate being pushed under another, or if you want to think about it, one plate riding up over the top of another. The place where it happens is called the subduction zone. That's the area where you get the one plate on top of the other. Now, when two continental plates converge, you got land, you got continental crust, and they hit one another, one goes up high, you get mountains formed. Now remember, not all the crust is continental crust. We're going to have some oceanic crust in there as well, but when you get a continental plate and another continental plate hitting one another, one goes up, the other goes down, and you get mountains. This is the reason why we have the Himalayan mountains. The world's tallest mountains are the result of two plates hitting one another. They're both land plates, they're both continental plates, and one gets pushed up high over the other. India has basically been slamming into the Asian plate or the Eurasian plate for about 75 million years. And as Asia keeps pushing into China or Tibet, it keeps pushing the land up. This is why you might have heard that Mount Everest is growing taller every year, because India is still continuing to push into China. Now, if I have an ocean plate and a land plate, if I get an oceanic and continental convergence, I get a little bit different result. What happens is you get a ocean trench as this starts to go down and it starts to drag a little bit of this with it, so you get a little deeper spot here in the ocean. That's called an ocean trench. Well, this land here is going to get eventually pushed up, and this friction here tends to make the land hot. It makes the rock melt, and then the rock, hot air rises, hot rock rises, kind of pushes its way up, and what we wind up with is a volcano. Now, those volcanoes can be dead now. They can be kind of out of their heat. So we're going to say this: we get volcanoes or mountains, and ocean trenches form when you have this kind of setup. Now, when plates move apart, they're together and they're starting to move apart, they're going to get thinner. Think about taking like a piece of bubble gum or a piece of taffy and you're pulling it apart. It gets that really thin part in the middle. Well, what's under these plates is magma. It's those gooey rocks from the mantle. And when the plates get thin, the magma can pop up in between. It can eat its way through that thin part. So what we have is we get volcanoes here, and then the volcanoes spit up new rock and the rock hardens. So we get new crust being formed when plates move apart. The Mid-Atlantic Ridge is one of the best examples on our planet of two plates that are moving apart. The Mid-Atlantic Ridge is a large chain of underwater mountains because this plate is moving this way. That's the Eurasian plate, or the African plate. And the North American plate is moving this way. So right here in the middle, we have a thin spot, and magma comes up and spits a whole bunch of new molten material into the water. Well, it's in the water, so it gets cold and it hardens immediately. What we end up with is a huge underwater mountain range in the middle of the Atlantic Ocean, and that is called the Mid-Atlantic Ridge. It's some of the largest mountains on our planet, but we don't see them because they're so far underwater. Iceland is a very interesting case study because Iceland sits right there on that divergent boundary. Half of Iceland is on the North American plate. The other half of Iceland is on the Eurasian plate. So half of Iceland is moving this way, and the other half of Iceland is moving this way. The country is being pulled apart right down the middle. And where it gets pulled apart, it's pretty thin, so magma pops up out of the ground and makes volcanoes and mountains. You can actually see this in Iceland. This is called the bridge between continents. And this is actually the Eurasian plate over here, and this is the North American plate over here. This is going this way, and this is going this way, and here's our rift in the middle. This is where Iceland is being pulled apart because it's on a divergent boundary. Now, if that divergent boundary doesn't happen in the water, if it happens on the land, what you wind up with is what's called a rift valley. A rift valley is when you have two continental plates that are pulling apart. The land sinks because it's thin. Sometimes you'll have volcanoes that pop up in there. But because the continental crust is 25 miles thick, it doesn't get as thin as the oceanic crust. The oceanic crust is only 4.5 miles thick, so you start to stretch it out and volcanoes pop up easy. It doesn't happen as easy with the continental crust. Now, the Great Rift Valley in Africa. Basically, this part of Africa is moving this way, and this part of Africa is moving this way or this way, and Africa is being pulled apart. And there's a very deep valley, very dramatic valley along those black lines. Well, eventually that valley is going to be deep enough that water from the ocean is going to flood in there, and this part of Africa is going to be a peninsula separated from this part over here. If you have a rift valley on land and it's someplace where it rains, the water is going to go into the lowest point. You're going to get a lake. Some of the world's deepest lakes are rift valleys that have filled with water over time. The Dead Sea is a very famous example. That's why the water in the Dead Sea doesn't make it to the ocean, because it's a deep valley in a rift between two land plates. The image on the right is Lake Baikal in the Soviet Union, which is the world's deepest lake. It was a huge pull apart in the land, and it filled up with water over time. Now, a transform boundary. Plates are moving side by side past one another. Our most famous fault, our most famous boundary, is the San Andreas Fault in California. This is what's happening in California, is that one half of California is moving north and the other half of California is moving south. Contrary to popular belief, California is not going to fall off into the ocean because this is a transform boundary. A divergent boundary, sure, maybe part of California would move here out into the ocean, but that is not what is happening. Rather, this part of California is moving this way, and this part of California is moving that way. That's called a transform boundary. All right, what I need you to do is, on a page in your notebook, in order to receive a done stamp for these guided notes, I want you to sketch the different boundaries on a blank page, or if you want to do it on 2 blank pages. They don't have to be pretty. You just have to have the right idea. And I'm no artist, so if I can draw these, and I did these on a computer, you can draw these. You don't have to color them. Here's an Oceanic-Oceanic Divergent. You see, we got under the water, the 2 plates are moving apart, and magma is popping up, and we're making new mountains and underwater volcanoes. Simple. We got Oceanic-Oceanic Convergent. Two ocean plates are meeting. We get a volcanic island because we get the friction here and the rock gets hot and the hot rock rises, gets up here, makes a volcano, and then we've got a volcanic island. A transform boundary. Plates are sliding past one another. Oceanic and continental convergent. Once again, you get the ocean trench and you get mountains and volcanoes formed near the coast. Continental-Continental Divergent. This is when we get a rift valley, which sometimes fills with water and gives us a nice big large lake. When you get two continental plates meeting, you get mountains formed. So that's the end of the presentation. You can get the done stamp after you have those sketches put into your notebook and you have the guided note sheet completed. At that time, I'll give you the notes quiz for today.